Uh, Let's see, the next item concerns alternative architectures. The first topic will be direct, and let's see, Steve Metschan is going to do that. Steve? Break here.
Great. Good afternoon, Mr. Chairman and members of the Commission. My name is Steve Metschan. It is my privilege to present the direct proposal to you on behalf of a courageous group of engineers and other concerned citizens. This began for me 4 years ago when NASA asked my company for an analysis of all possible approaches that could meet the policy objectives of the VSC, or the vision, within the available budget. This analysis was refined and transformed by government and industry experts into the direct concept I'm showing today. Next slide. The direct plan is intended to help put the U.S. exploration plans back into alignment with the approved policy and within the limits of the available budget. The reductions in long-term discretionary spending make this even more imperative today. So what is the Jupiter? Jupiter is based on the space shuttle. The space shuttle is the horse we are currently riding today into orbit and represents a good foundation from which to create a new capability for the future. Jupiter retains the proven and already man-rated shuttle main engines and the solid rocket boosters. Now, ironically, the first thing all shuttle-derived systems do is they remove the shuttle. But they retain the heavy lift stack that has taken us to orbit now for almost 30 years. The primary modifications to the stack is to use the tooling at Metschan to actually produce the oxygen tank to turn it into an inline vehicle in which the core becomes the carrier for the payload. The primary new piece of structure we need is the aft thrust structure. We then replace the shuttle main engines that are already flying, the existing 4-segment rockets, and we produce what we call the Jupiter core once we add the payload adapter and the avionics. Above that, we put the payload, which is completely separate from the spacecraft, so it does not affect the abort capabilities for that. And with the payload fairing, that's our entry-level vehicle, what we call the Jupiter 130, or some may want to call someday the Ares 3. Once you're at that point, we add a planned addition 4th engine to the core, which is already designed to handle the additional loads associated with an upper stage, which could be J2 or RL6 based. The avionics ring is then replaced with the Altair lander, payload fairing already developed with Orion, and that becomes Ares for the Jupiter 246 in this particular configuration. Direct is not a new concept. Next slide. Even before the shuttle first flew, NASA engineers suggested utilizing the hardware and infrastructure of the shuttle to develop a derivative heavy lift launch system. Following Challenger, NASA engineers once again studied this idea in even greater detail, ultimately recommending the National Launch System, or the NLS, which passed its preliminary design review milestone in 1993. Now, in a post-Columbia world, some NASA engineers have once again asserted, at great risk to their livelihood, that the best path forward is still a true direct, hence the name direct, shuttle derivative. Given the imminent destruction of America's second heavy lift system and infrastructure, this commission will ultimately help determine if a solution repeatedly advocated by NASA engineers over the last 30 years as a practical solution to America's heavy lift requirements will ever become reality. Next slide. The engineering feasibility, use of available tooling, flow within the existing external tank manufacturing facility, and transport of an inline core has been assessed in great detail by NASA repeatedly. In fact, the National Launch System Study produced a series of detailed studies of which the core alone had 1,000 pages of detail associated with the design and how one would accomplish that. Then as now, the most time-consuming and risky element of any rocket development effort is still the rocket engine, not the tank structure. Direct is the only man-ratable proposal on the table with man-rated rocket engines already flying, namely the shuttle main engines. Now, some have said Direct is nothing more than paper rocket. Nothing could be further from the truth. Currently, the Ares 1 requires a new 5-segment solid rocket booster development. The Jupiter's 4-segment SRB is already flying on the shuttle. Ares requires a new upper stage engine development, the J2X. The Jupiter's engine, the shuttle main engine, is already man-rated and flying on the shuttle. Ares 1 is currently struggling to mitigate the serious thrust oscillation issues associated with an unproven configuration. The Jupiter's configuration utilizes a proven approach for dampening these vibrations. The Ares 1 requires a new launch infrastructure, whereas the Jupiter uses the current infrastructure while also incorporating cost-efficient improvements to the current side-mounted approach. The Ares 1 requires a staging event, whereas the Jupiter's main engines are ground-lit just like the shuttle before committing to launch. The Ares 1 lift limitations has required key safety mission systems and redundancy to be eliminated from Orion, while forcing the same to endure an unprecedented vibrational environment for a lunar spacecraft. Jupiter has more than enough margin to put all these safety systems back in. Taken together, all the development costs for the Ares 1 makes it substantially more expensive to develop while simultaneously increasing both schedule risk over the Jupiter. Bottom line, we believe strongly that the Jupiter will close the gap within the current budget. More importantly, to see what we're getting for our money, with Ares, though I realize Ares develops a lot of technologies for the Ares 5, we'll get to that in a second, but with what we get out of the gate here, with Ares we spend about $14 billion for a launch system less capable than what we can buy today. Whereas with the Jupiter, while we spend $8 billion, we get a launch system that will be second to none in the world, while increasing substantially the crew safety. So let's look at the basic overview here. Ultimately, even our entry-level Jupiter, which has no upper stage, will offer a capability that no one else in the world has, especially in terms of volume capacity. But when it comes to lift capacity, we have roughly 3 times as much mass performance as the next largest operational launch system, the Delta IV Heavy. Next. It is also important to point out that the current plan requires the development of an even larger launch system than the Ares 5 that promises to bust the budget and will also require the deorbiting of the International Space Station 2016 in order to free up the cash necessary to pay for its development. Under the direct proposal, the only new component we require is an upper stage in order to deliver a sufficiently high performance, lower cost, and more flexible lunar architecture enabled by operating one launch system but launching it twice. While certainly not as inexpensive as abandoning the vision for space exploration and remaining in low Earth orbit for another 30 years, it is significantly less expensive than the current plan. Because the Jupiter's main engines and solid rocket boosters are already finished, our schedule and budget are not dictated by such costly and high schedule risk items. By stretching out the remaining shuttle flights by 1 or 2 years, we can deliver a significantly smoother and therefore safer flyout of the remaining shuttle missions by providing a future for the operations workforce we are depending on right now to stay at their posts despite our lack of commitment to them. Direct can do this even in the tough budget environment before us because the shuttle workforce in a direct approach is an asset we need in order to conduct the Jupiter test flights themselves and not a liability to be eliminated in order to fund the development cost of Ares. The primary tent pole for initial operating capability for the Jupiter to the IS is not the launch system, but is in fact the Orion spacecraft. Ultimately, while the transition will not be pain-free by any means, America will have a much more capable system sooner than any other plan on the table at the end of that transition. A lot has been said about the importance of crew safety during the ascent portion of the mission. Yet, ascent risk represents a very small portion of the overall mission risk for beyond Earth orbit destinations. For these missions, it is in fact the redundancy and margins of the crew spacecraft that determines the overall mission safety level. Due in part to the Ares 1's limited lift capability and unprecedented vibrational environment, Orion has been forced to remove important safety systems and reduce overall redundancy. As a result, the overall crew safety has been significantly reduced during the whole mission, not just the first 8 minutes of it. The fact that the Ares 1 is composed of unproven systems, whereas the Jupiter is largely composed of existing flight-proven systems, only casts further doubt on the Ares 1 safety claims. Regardless, the Jupiter enables all the safety systems that NASA originally wanted on Orion, not the least of which is returning to the land landing capability once again for every mission. Even our entry-level launch system, the Jupiter 130, that's the system without the upper stage, will provide a remarkable range of new capabilities. For example, currently there is no way to repair or upgrade the James Webb Space Telescope. With direct, a servicing mission could be conducted using the Jupiter 130 to place both crew and equipment into a high Earth orbit, rendezvous with the telescope, and repair it in a similar fashion to what happened with Hubble, only in a much higher orbit. The same capability could be used to assemble a network of extremely large 12-meter diameter telescopes, enabling the ability to resolve other habitable planets in our galaxy, answering a question as old as mankind itself: are we alone? The Jupiter's increased payload diameter enables robust Mars sample return missions that would pioneer new entry and descent landing systems needed before we can ever land astronauts on Mars. On Earth, everywhere we find an energy source and liquid water, we find life. With our entry-level Jupiter, we enable the Earth departure mass required for these kind of large missions to the Jovian moons in order to find if a second genesis has indeed occurred within our own solar system. By removing the barriers that limit all future exploration, the Jupiter will ensure that NASA and therefore mankind's best days of discovery clearly lie ahead. As Carl Sagan once said, somewhere, something incredible is waiting to be known. The Jupiter 130 will also enable new missions to the planet Earth, starting with an inspirational mission that originally went to explore the moon, yet ended up rediscovering the Earth. As a man-made spacecraft, look back at Earth in 1968. All of mankind became aware that we are all astronauts and drove home the importance of protecting our delicate spacecraft world for this and future generations. We are quickly approaching a time where the majority of people on Earth were not yet born to experience, myself among them, this profound mission themselves. You would find it just as remarkable as the previous generation did. One potential Earth-focused use of the Jupiter 130 would be to launch space-based solar power systems in one ground-integrated package that can deliver environmentally friendly energy from space 24 hours a day. The same telescopes developed to discover the signs of life on other planets in our galaxy could also improve the resolution of Earth's climate by many orders of magnitude. With this increased data resolution, climate models could be significantly improved in accuracy, helping to guide trillion-dollar decisions concerning the environment. And of course, there are national security reasons to improve our ability to look back at Earth from space as well. It has been asserted that any system based on the shuttle will be just as unaffordable as the space shuttle. Nothing could be further from the truth. The cost breakout of the shuttle shown here is based on almost 3 decades of hard cost data generated by a mature system. Because the Jupiter is so closely associated with the shuttle, we can, with a high degree of confidence, predict what the cost structure will likely be for the Jupiter. Once the cost associated with the orbiter and crew training is removed, the cost of a cargo-only launch of the Jupiter 130 would be about 72% of the current shuttle. A step in the right direction, certainly, but not a large cost reduction. The primary improvement in the cost effectiveness in going from the shuttle to the Jupiter is not from the reduced cost, but from the increased lift capacity. By removing the dead weight of the orbiter, we can achieve almost a 5-fold increase in lift capacity. Taken together, the Jupiter will deliver almost a 7-fold improvement in dollars per kilogram delivered to orbit compared to that of the shuttle, dropping it almost below $5,000 per kilogram to orbit, a very competitive price indeed. Slide. The cost benefits of the Jupiter go well beyond launch cost. The Saturn V was the first and last time America had access to a high-volume, heavy-lift launch capacity. With the Saturn V, we were able to launch ground-integrated, more capable spacecraft into space using only one launch. After destroying our first heavy-lift launch system, we were then forced to assemble large spacecraft like the International Space Station in 20-ton chunks. Mike Griffin had it right when he said this was a step backwards in terms of cost effectiveness. Unmanned exploration experienced the same dynamic, with the development cost overruns of the James Webb Space Telescope and the Mars Science Laboratory now running many times their respective launch costs, due in part to trying to shoehorn more capability into existing launch systems' capacities. It pays to use the right tool for the job. To grow beyond our past impressive accomplishments in both manned and unmanned exploration, America needs the Jupiter. NASA is on record of claiming the Jupiter cannot achieve a self-imposed performance objective that NASA has seen fit to place ahead of the real requirements of budget and policy. In fact, they took one step further and claimed that Jupiter actually violated the laws of physics. Yet, the recently leaked ESAS appendix shows that a lower performing configuration of the Jupiter will actually exceed NASA's self-imposed performance objective even while burdened by an inefficient upper stage design. A self-imposed performance objective that the technically challenged Ares 1 and the budget-busting Ares 5 still cannot achieve. Not only does DIRECT meet NASA's desired lunar performance objectives, but DIRECT will place NASA back within the confines of policy for a price we can actually afford. Based on this track record, we strongly recommend that this commission get a second opinion on the upper stage design by talking to experts at the United Launch Alliance. Engineers like Bernard Cutter have decades of experience designing, building, and flying advanced upper stages, something that NASA has not done for nearly 3 decades. In fact, we would recommend a second independent expert opinion be sought on all critical issues brought before the commission. What about the performance needed for Mars, though? This issue was addressed over 46 years ago by none other than Wernher von Braun himself, who had always dreamed of one day seeing man land on Mars. He said that once you reach the limit of whatever launch system you can afford, you're left with 2 options for increasing performance. The first option is what he called connect mode, where you assemble various spacecraft elements in Earth orbit. The second option, though, is called tanker mode, where the spacecraft is launched in one-piece dry if necessary, without propellant, but is then filled in orbit with propellant prior to departure. Von Braun clearly preferred tanker mode because he correctly understood that most of the mass needed for a Mars mission is, in fact, propellant, not spacecraft. Therefore, propellant is the primary component that we need to assemble in orbit. Well, the best way to assemble propellant in orbit is with the propellant depot, Propellant Depot has a number of advantages, not all of them technical, some geopolitical as well. The Propellant Depot increases mission flexibility while opening up almost 70% of the mass required to commercial and international supply. In addition, one future option for potentially lowering the cost of space exploration is by producing propellant from the Moon, Mars, or other suitable bodies throughout our solar system. A critical first step, though, is the ability to store and transfer propellant in space. The Propellant Depot is also a critical step for lowering exploration costs still further by reusing the very expensive spacecraft, thereby eliminating the need to throw away these expensive systems after each mission. The utility of the Propellant Depot will also naturally attract international participation and funding as it improves the capabilities of all partner nations. Bottom line, once your volume capacity is sufficient to launch ground-integrated spacecraft as one unit, your launcher is large enough. The Saturn-class Jupiter is more than sufficient for the exploration program, while also having a lower fixed and variable cost than the Nova-class Ares 5. On the other extreme are those that would advocate an exclusive ELV COTS program, thereby resulting in the destruction of America's second heavy lift system and workforce. The direct plan meets that team more than halfway by opening up 70% of the mass needed in orbit to competitive bid. In addition, a significant barrier to entry for new companies and approaches is removed because cheap propellant is less expensive to insure than expensive spacecraft or people. Unlike opening up a few flights to the International Space Station per year, this approach represents more than enough demand to max out the launch capacity of most ELV COTS providers, enabling them to achieve the economies of production associated with high launch rates, lowering the cost for all their customers. Establishing an in-space market for propellant will also help build the business case to commercially develop propellant from the Moon as well. It has now been almost 4 years since the basic of what I just presented here was first shown at NASA headquarters, but unfortunately rejected in favor of the Ares 1. Even now, because so much of the hardware, infrastructure, and workforce are still in place operating the shuttle, Direct can be available much sooner while also delivering a significant increase in crew safety over the shuttle. Direct not only builds upon this existing multi-billion-dollar heritage, but simultaneously accelerates the progress already made by removing the bottleneck of the Ares 1 for IS access and retargeting its developments already underway for the subsequent lunar phase of the vision for space exploration. Ultimately, we strongly believe that Direct is the only way our nation can hope to achieve the policy objectives within the limited budget we have before us. Direct will not only solve the looming issues facing the manned space exploration, which is the goal of this commission, but will present a new opportunity for unmanned exploration as well by removing the limits imposed by existing launch systems. The ability to lead from the front in capability will naturally attract other nations to join the American-led efforts and to a truly global effort, while at the same time providing a serious opportunity to the commercial sector to deliver most of the mass needed for the vision over the long term. Taken together, we strongly believe that Direct is by far the best possible path to ultimate success for NASA, which is what's motivated the Direct team from the very beginning, America, mankind, and in furthering space exploration and development. I carry 3 requests from the Direct team to the Commission. The first request is the Commission ask the President to order NASA to cease any further destruction of the shuttle infrastructure until this Commission can make its recommendation to the President. Our second request is that the Commission endeavor to talk to the engineers at the working level of the Ares 1 technical problems and the Ares 5 cost problems as anonymously as possible in order to determine independently for themselves the ground truth of the present program. We have certain knowledge that this ground truth is being altered as it ascends the chain of command, and there's a significant amount of pressure being brought to bear to prevent any information from being providing to this commission that is counter to the current party line. Our third request is for the commission to get a second expert opinion on all critical issues or disagreements NASA may have with our plan, like the upper stage, for example, from sources independent of the current NASA chain of command. I thank you for your time, and I welcome any questions you may have.
Thank you very much. Those are very serious charges, as well as a very serious set of performance and cost data you've offered us. Let me ask if my colleagues have any questions to begin with, and I have one. Yeah.
Yes, sir.
Steve, you may not be the right person to ask this, but in the ESAS study in '05, the sort of something that looked pretty close to this, two-launch, 70-ish ton vehicle was pretty closely looked at, and in fact carried as one of the options, at least in the first and second cycle of the ESAS study. Do you understand what the rationale was in the ESAS study that caused the decision to be made into the so-called 1.5 launch options, as opposed to the sort of 270-ton class launches? And what would your response be to that rationale?
I probably can't explain it to you because I don't understand it myself. I think it makes a lot of sense to develop one. We really only have the money to develop one launch system, and I think the efforts of SpaceX and the efforts with the ELVs and the COTS program are more than adequately covering that class of launch systems that the Ares 1 represents. I think NASA's right position is to work on a heavy launch system. I would also suggest that the current Ares 5 has gone a great distance away from the Ares 5 that they recommended. The Jupiter is closer to the original Ares 5 than the current one. It uses shuttle main engines. We use 4, they use 5. Again, our main contention really is the Ares 1, not the heavy lift capability. And our only recommendation is the heavy lift capability needs to get back to a true shuttle drive system.
Thank you.
Yeah.
Jeff?
I've got 1,000 of them, not just one. So I'll ask a meta question first.
Get
Just
one.
let me get back
Yeah.
to you with more questions.
Yes, definitely.
Okay, in that case, I'll pick only the highest one, which is, I'm well aware of the many advantages that you get from a propellant depot architecture. And I understand the concerns about the workforce, but set that aside for a moment. If you are going to do a depot capability, why not go farther? Because when you look at any of the systems architectures I'm familiar with, the spacecraft dry already fit on EELV-like objects.
They do mass-wise, they do not volume-wise. People keep forgetting the importance of volume. When I saw some of the Delta heavy configurations, they kept the same 5-meter. Yeah, if it's a big sack of hammers we're putting up there, they're probably right, but the average density of payload in space is about that of balsa wood. So you got to keep that in mind. You got to grow your volume at the same time you're growing your lift capacity, and the Jupiter does that.
Thank you.
Please, Leroy.
Yeah, I just have a question about who are you guys? I mean, is there a list of folks who are? I mean, I understand what you're saying about wanting to be anonymous, but are any of you besides you willing to be identified?
Well, when you find them, let me know, because I don't know them all either. In fact, none of us do. We're taking advantage of the new communication technologies that became available with computers and the internet, which I think is why going forward after this point, and we fully intend to abide by the recommendations of the commission. This is not. There's no way to make money at this, by the way, of disagreeing with your customer. But
it's just difficult to assess the work without knowing who's doing it.
Well, we can get you names of people to talk to, but the anonymous part is critical. There's a certain amount of blood in the water, if you will. So I just think it would be, if we want to get to the bottom of what's going on, I think that's the best policy. I think that's the great thing about this commission, actually.
Bo?
Yeah, Steve, well, I'm impressed with your enthusiasm and with your boldness, But I do have one question. Your charts are not numbered, so this is a pie chart that talks about your Jupiter and STS cost comparison.
Yes,
Can we get the chart back for a second?
I think it's about, what, slide
About halfway
14 or
through the
so?
deck.
Well, let me go ahead with my question. You compare the current STS to your Jupiter 130, and you're saying the cost of 5 flights, I believe, is 2.6 billion, and you contrasted with only 1.9 billion for Jupiter.
Correct.
But shouldn't you include cost of 5 Orions if you wanted to have like apples-to-apples
Well,
comparison?
this is a cargo version.
Well, you know, but you're comparing it to a vehicle that carries 7 astronauts also.
Actually, that's one of the big advantages of this approach. We can fly with a crew or not. And so we have both a cargo version and a crewed version. Obviously, if you fly with the crew, any launch system will be more expensive than if you don't fly with a crew. That's one of the utilities of this approach.
Okay, so this is a cargo version, you're
Correct.
comparing it to a crew-faring
But
vehicle.
that's the interesting thing about the shuttle. They combined cargo and crew together.
Right.
Which not only affected the safety and the abort possibilities, because our cargo is carried below the crew. If the crew comes along with the mission equipment, they're carried below it like Apollo, so they are unaffected by their abort. So we believe that was the fundamental recommendation from the Columbia report. Let's not have such a large launch system that we can't quickly and safely extract the crew should something go wrong. Likewise, it works on a cost basis, which means now you can have a cargo version that's less expensive and also fly crew when you need to as well.
Okay, thank you. Thank you.
Chris?
Yes, you stated that the Jupiter system would represent an improvement in crew safety with compared to the shuttle. Could you quantify that?
Well, right away, if you assume we had the same safety levels as the shuttle, the 2 accidents that we know of, the Challenger being the SRB leaking, could have been abortable had we been watching for those kinds of things, the leaking SRB. And then, of course, in the Columbia accident, the heat shield's entirely protected during the ascent. So just having a quick escape system on the shuttle, which we currently really do not have, and assuming that's 1 out of 10, it fails 1 out of 10 times, you get a 10-fold improvement. Now, I'm glad you brought that up because there's another big advantage. In our architecture, even in a lunar program, half the time we're launching uncrewed. So as long as the vehicle's being processed and treated as if we have a crew on it, the probability of an accident occurring on a crewed flight is naturally cut in half. That's one of the advantages that the EOV and the other programs have, is that they're essentially continually testing the entire system, which is not just hardware, it's people, the culture. Every time they launch, they're testing everything. Many times these hardware safety-based assessments, I think, are incorrect. When we look at the accidents that have happened, they've been an impact. They've interacted with the hardware, certainly, but there's a certain aspect of culture that came into it.
Okay, I'll take the last question, I think, if that's all right with the group. Many years ago, NASA looked at a configuration quite similar to the Jupiter 130 that, based on the external tank, the solid rocket motors, and so on, and didn't continue it. With your folks' apparent background and knowledge of NASA, do you have any idea why that was dropped?
I think they didn't want to operate both. They didn't have the money to operate both the shuttle and that system at the same time. I think now that the retirement of the shuttle is now official national policy, we can now afford to entertain. It keeps coming back to the same principle. I think we only have the money to operate one launch system, so let's make it as capable and as expandable as we can. And I think the inline version of a shuttle drive system achieves that objective.
Well, thank you very much for your presentation. We will take it very seriously.